All right. So,
okay, so yeah, George will tell us, will give a talk about scientific project reproducibility. So the stage is yours.
Thanks so much. Well, thanks everyone for sitting in. Sorry for the turmoil, so to speak. But I'm very glad to talk about this subject because it's really dear to me, and I'm thankful to Thomas for inviting me. We are switching gears. I'm not going to be talking about high energy physics. I'm going to be talking about reproducibility in science, and particularly in computational science. So to set the stage for this talk, I want to mention this survey that has been done from Nature some years ago that was asking a simple question: is there a reproducibility crisis? And to about 1,500 scientists, and unsurprisingly, the overwhelming majority answered yes in some extent. And if follow-up questions asked, where does this come from? There are many, many reasons, but the ones I will focus on would be the methodology and the code aspect and sharing code. So it appears to me and to many scientists that reproducibility is a real problem that we're having in academia right now. And my goal always in this subject is to, instead of complain about it, like you see on YouTube all the time, to just try and make something out of it and perhaps educate our own selves how we can do better reproducible science. I'll start right away with what I hope to convey with this talk. And to be totally honest with you, what I'm hoping is that you will find this talk extremely boring. Yeah, you heard this right, because I'm hoping that what I will say you already know, and you have already embraced this lifestyle of reproducible science. So for me, the best outcome would be that you will be bored by this talk because you know everything. But of course, in case you haven't heard of some of the points I will bring up, I'm sure there is plenty of gold to be found in this talk. So what are the three key things that I hope that you will take from this talk and remember when you go home? The first is that reproducibility is something that is fundamentally important for trustworthy science. The second is that reproducibility is a matter of habit and not a time sink. So it's like brushing your teeth, and once you learn about it, it becomes second nature and doesn't cost you resources or energy. And the third thing is that there are tools that offer streamlined, reproducible scientific workflows. So if you phrase this all together, what I hope that you will see is that this is really a matter of education. So if you learn the true Jedi way of how to do this, it becomes second nature to you, and it all works out nicely in the end. This has been my experience so far, teaching people and students the reproducible way. I just want to clarify that my talk will be about computational sciences. I'm not an experimentalist, so I'm really not qualified to instruct anyone on how to make reproducible real experiments. Okay, now why do we want reproducibility? Because I think deep down we all want trustworthy and confident science. When I think of trust in science, I think that on one hand, we hope that the researchers do their stuff correctly, but they also allow us, the reader or the receiver of the science, to examine their work openly, besides this trust. And when I think about confidence, I'm thinking that when a scientist presents some scientific claim, this claim is robust with respect to expected natural variability in statistical variability, random number variability, or variability of the used computational algorithms. Now, the key thing in all of this is that reproducibility is actually a prerequisite for either of these aspects, because how can I possibly trust someone that they do their stuff correctly if I cannot redo exactly the same stuff they did? And how can I check that the results are confident and robust if I cannot reproduce the results in the first place to then change some computational aspect? Just for these whole two reasons, I think we should really be aware and care about reproducibility. And I'm not even mentioning a whole baggage of other reasons like accessibility or respecting the public or future collaborations and many other reasons. So reproducibility is important. And now in the rest of this presentation, I'm going to outline some key tips I have collected over the years of what makes reproducible science easier. And the first thing, and by far the most important one, is to share your code. So I stand to claim that the only way for 100% absolutely true reproducibility is to share the code that you used. And there are mainly two reasons for this. The first is that a human language-based description of what code does is almost always not enough. I'm using here an excerpt from a paper I use in my workshops that practically describes a computational process that these authors have used. And if you read this carefully, you will realize that there are in fact many parts of this text that are not precise enough. So if you try to write a code that does the thing, you would realize that you could not do it because there is not enough precision in this claim. And I also want to highlight something that I find often, I read very often in published research, even today, which I find completely ridiculous, which is to say, we used Python to do our analysis. I find this ridiculous because this is really the same thing as saying we used a computer to do our analysis. So it is such a generic and vague statement that it doesn't convey any additional information to help you. There's a second reason why you should absolutely share your code, and that is that it is often the case that a variable value or a parameter value will be forgotten in text. And this is very common. It has happened to me and to many, many people. But the key is that by definition, code does not run unless all variables have a value. Otherwise, it would error, right? So if you share the code, you're kind of guaranteeing that you have not forgotten anything. I just want to repeat this, that please always share your code. Even the ugliest code in the universe is so much more useful than no code at all. So this does make a big difference. So that's tip number one. And tip number two is what I call the principle of least gears, which is practically means if your job as a scientist was to come up with a device to blow your nose, the best way to do this based on some criteria would be to just take a napkin. And a bad way to do this would be to create all this ridiculous contraption for blowing your nose. So the rule of thumb that I want to present here is to use to minimize the different gears, so to speak, that you use in your project. So if you could use a single programming environment for literally everything in your project, then you should do this because this makes it much more likely for your project to be reproducible. I'm having here a typical example from a place I used to work where you would use Bus to submit jobs to a cluster. You would use 1 trillion lines of code, Fortran code to simulate climate. You would use a C command line tool to process the climate output. Then you would use Python to analyze the simulations. And then you would use some archaic library to plot maps over the Earth. So this is 5 different gears. And this is actually a real workflow. Or you could use Python for everything besides perhaps the Fortran aspect. And this is useful because the reader or the receiver of your science has to only read a single language and only run a single language. So just to be clear, I know that this is not always possible, right? I'm providing some tips here, and sometimes this will be applicable, sometimes not. If this is applicable, I think it's a good idea. Tip number 3, by the way, I will summarize the tips at the end, so don't worry. But anyways, the talk is recorded. Tip number 3 is to have a consistent and coherent project structure. You should try to follow the same structure for all of your scientific projects. Why? Because this makes everything more organized. And things being more organized means that they are much more likely to be reproducible. What you saw on this, what I show here on the right-hand side is the recommendation from Dr. Watson that I will present later on. I just want to be clear that there is no golden standard here, right? There are many different templates and different packages that provide templates. So the goal here is to pick your favorite and stick with it. Really, the thing that is important is the consistency, so that you organize your scientific projects well, and you can share them easily with people, and people know where to find your stuff. We go now to number 4. That might be surprising to some of you. It's definitely surprising to people where I'm typically working, and this is to use notebooks appropriately. Here with notebooks, I'm referring to this new type of mixed media like Jupyter or Pluto, which is a way that you can program that interlaces code and markdown and figures all in one document. So this is really fantastic. But I would argue that notebooks are very good for presenting material, but they are not good for creating a code base. What does this mean? This means that you should not abuse notebooks for doing research. And there are a couple of reasons why you should not do this that I am summarizing here. The most important of which is that notebooks are kind of isolated environments that don't play very well with other notebooks. Like you cannot include notebooks in other notebooks. It's difficult to version control notebooks. Some notebooks have hidden variables. So this kind of self-contained environment is not very, let's say, useful for developing a code base and for establishing a reproducible workflow. My counter suggestion to notebooks is to still use them for example, structuring reports or drafts, or creating plotting scripts where you will visualize the same, you will use the same visualization process again and again, or for presenting your work. But a good rule of thumb is that if you have been using the same notebook and developing work on this notebook for a week or so, it's a good indication to drop the notebook and go back to writing a source code base that you can call upon in your scripts. And for that, I would advertise to use a high-quality IDE, integrated development environment like VS Code for your day-to-day work so that you can establish a code base. And I just want to emphasize that these modern coding environments are really very, very powerful, and they allow you to do really crazy things, even create Jupyter notebooks entirely within them. Number 3 was to take notebooks appropriately, or 4, I'm not sure. Maybe this is tip number 5. I have them summarized at the end, don't worry. And it is about keeping things simple honesty. So this means that you are faced with a situation where you are considering to create a new data structure in your code. And what I would say in this scenario is to always ask yourself if this is necessary, or if one data structure that fits your needs already exists in a package. So what I'm advocating here pretty much is to not reinvent the wheel. If you want a named parameter container, probably a dictionary is already good enough. Or if you want something fancier, maybe a package already exists that has this. Python users, similarly, you shouldn't be creating new classes for one single task that could be a function instead. So favor simpler and native data structures. Of course, I don't want to mislead you. There are always situations that creating a new data structure is the way to go. Particularly in Julia, this is a key thing for multiple dispatch. And typically in performance optimization, you would need a specialized data structure. But just the rule of thumb is to not reinvent the wheel and always challenge your own self. The moment you try to code something new, just challenge yourself and say, could I be using something existing instead? This helps with reproducibility because the more existing things you use, the more things that have been tested you use. And this tend to last or to stand the test of time longer. Okay. Tip number 5 is deterministic code. So most computers that exist at the moment are deterministic, and you should abuse this fact to also write deterministic code. So to understand how this works, we need a very quick primer in random number generators. With the exception of some true entropy sources, random number generators are not actually random. They are deterministic devices that simulate randomness. Most random number generators are actually chaotic maps. So they are chaotic dynamical systems, but given a number, xn, they generate a new number, xn plus 1. And this way, starting from a single number x0, you generate a sequence of numbers x1, x2, etc., by plugging the result into this chaotic function. And the way this is useful is because it turns out that the sequence of numbers is typically distributed uniformly and sufficiently randomly in the unit interval. When you as a user ask Julia or any programming language to give you a random number that is that is normally distributed, this is what actually happens under the hood. First, a global random number generator is initialized or is obtained. This random number generator is then called with a particular starting seed, or if it is already initialized, it's called with its previous seed. So this seed is then given to this chaotic function or any other function, and it generates the new number, x1. And then this number x1 is distributed uniformly, but then you simply transform this distribution into the normal distribution in this example by using the cumulative density function of the normal distribution. So random number generation is an entire field, and here I have super duper simplified, but this gives you the main idea. What does this mean for you as a user that cares about reproducibility? Well, if you use randomness in your work, you should explicitly use such random number generator objects. For example, in Julia, instead of saying x equals rand, and that's it, you should use the random package of Julia, initialize a random number generator explicitly, for example, one that is called x00, and then call the rand function again, but give it explicitly this random number generator. This is really cool because not only it is transparent, but it is also better for performance. It allows people to check how valid your results are by changing the seed, but it also allows reproducing exactly the same randomness that you use in your work by using the same seed. So this is very nice. All right, how are we on time? Okay, I think we are very good on time. I'm halfway through, but I'm definitely 2/3 of the way in. All right, so that's something I think most scientists have felt at least once in their lives, where someone gives you a project that it works on their machine, and then it doesn't work on your machine, and you say, oh no, it doesn't work, but they say, oh no, it works on my machine, right? So you really want to avoid this hellhole. This is how I call this place. It's a really dark place. The way to avoid this is to detach, or by detaching your project from your machine as much as possible. So how do you do that? There are two main ways to go about this. The first is to bundle your project with a list of versions of every package you have used in your project, including their dependencies. And I'll show you in the next slide how to do this for Julia, for example. But of course, this also means that your own code has to be versioned, right? So you should be using some kind of version control system like Git and track the changes. You don't have to version it with numbers, just Git it by itself is already good enough for this particular purpose. The second way that you can avoid this works only on my machine problem is to avoid entirely absolute paths. So try to create a root folder that contains your science project and try to call everything with respect to this root folder using only relative paths to the root folder. And I will show a software in a moment that helps with this. So this is a nice meme that I use in my workshops. This is a very good teacher over here that shares this nice document with students, but of course this document is actually an absolute path in the computer. So it doesn't really help anyone, but this happens all the time when you share your code and it tries to load a script or a data file from an absolute path. I've mentioned that you should list the package versions that you use. There is a versioning system called semantic versioning 2.0 that is very nice, but actually I won't go through this slide because this slide is interesting only if you're a developer of software. If you're only a user, then you don't really have to care about this, and you only have to know about the versions that people use. So I'm skipping this slide, but of course you can find it online. And now we go to tip number 7, which is one science project should be one environment. Environment is a concept that most programming languages have built in. And an environment is a self-contained space where one can add packages and track package versions and specify compatibility bounds to packages. And once you activate this environment and you try to use a package using an import or using statement, this means that you will use the version of the package that you have specified in your particular project. And of course, you can share this entire project to your collaborators, and they can just instantiate this project, and their project will work like it did in your computer, fingers crossed. And this allows, of course, for reproducible code because it ensures that everyone runs the same package versions. And therefore, you won't have errors that the function doesn't exist because they are using an older version of a package, for example. by default, of course, when you start your programming language, there is this global environment that is activated, but I believe and I advocate that you should not be using this environment for scientific work. So my claim here is that each project should have its own environment, and this allows confidence that each project doesn't break over time as well, because you have updated another project. Well, one project is completely self-contained, so it doesn't matter if you update something else. To create an environment, this is very straightforward in Julia. You just create, you just use the command package activate. I mentioned that you should be bundling this self-contained project of yours with package versions. The way this is done in Julia is that once you create this self-contained environment or project, you have this project YAML file that establishes reproducibility. So Stefan has already presented this, so I can go fast. This is simply a file where you enlist the dependencies of your project, and optionally you specify compatibility bounds for each dependency. And then you can share this to your friends and family, and they can just do package instantiate, and then they will get the same version as the ones you used. So this is super duper cool, and I have to say, Julia is unbelievably strong programming language for this type of reproducibility. Okay, so now we are out of the text, and what follows is pretty much an advertisement, because I want to share with you Dr. Watson, which is what we call a scientific project assistance software. And of course, disclaimer, I'm one of the developers, so this is definitely advertisement, but we genuinely built this software to make managing scientific projects easier. Thomas is also one of the developers, so feel free to chat with him more once I'm gone and I cannot see anymore. Yeah, so Dr. Watson is a package for the Julia programming language that is used within the language. So it is not an external tool, it is not a command line tool, it just offers functions that you just use within your scripts, just like any other function. Just like you would use the solve function for differential equations, you would use the save name function from Dr. Watson. There is a summary of the many things that you can do with Dr. Watson that I will not go through because I will present some examples. And I have to say that last time we checked, we didn't find real alternatives to Dr. Watson in other programming languages. So I'm sorry to Python users, but maybe there aren't many in the audience. There are some other software that can help you with streamlined, reproducible scientific workflows. Sorry, give me one moment. All right. Yes. So the first thing that's very cool from Dr. Watson is that it assists you very much on this bundling your scientific project in one place and avoiding the problem of it runs only on my machine. And it does this by providing two functionalities. The first functionality is what we call quick activate. So quick activate is a function or a macro that you put at the very start of your script. And the way this works is that it reads where your script is located on your folders, and then it scans your folders for a project YAML file. And once it finds the project YAML file, it activates it. So in this way, you activate your scientific environment immediately before doing anything else in your scientific project, and this ensures that everything that you do is self-contained. The second part of this aspect of Dr. Watson is the project dir functionality. That is, in fact, very simple. It ties well with quick activate because the way it works is that once you call the project dir function, this simply returns for you the directory of the currently activated project. And if you call this function after quick activate, this directory coincides with your scientific project environment. And there are derivative functions like data dir, or you could put arguments into these data dir functions as if you use the join path function. And what this does, it ensures that you only have to use local paths, relative paths on your scripts. And these functions translate these paths to absolute paths so that you can load files. But of course, when you share this and you give it to another user, the functions will automatically create the absolute paths for another user and in another computer. I would say this functionality is so good that both me and Thomas agree that we would use Dr. Watson even if this was the only thing that it offered, because it makes everything so convenient. The second aspect is including Git information in saved output. So I like to think of Git as the time travel of coding. I really like this aspect of Git. And this means that if you make your scientific repository a Git repository, then you could also have time travel of your scientific results. So this is super cool. And Dr. Watson offers the TagSave function. The TagSave function is simply a replacement of the standard save function that you get from file IO in Julia, which is the function that you just save data to disk. If you use the TagSave instead of save, then what this will do for you automatically is it will attach two fields for you. One field is called git commit. That is simply the current commit of your scientific repository or the latest commit. And the other field is the script field that tells you where was this script located and exactly which line of code was the command TagSave saved at. In this way, when you load some scientific result you have saved, but your code base has changed completely and you're not sure how you created these results, well, you can find git commit and then go back in time and see the code base as it was when you created these results. And the last feature from Dr. Watson I want to highlight is something I use very often in my work, and it makes my work very nice and streamlined, which is some quality of life functionality for simulation input and output. If you are a computational scientist like myself, what you typically want to use is create a main function that does some kind of simulation, but then run this main function for many different combinations of parameters. It's this nice dict list function that its goal is to help you prepare many different input dictionaries that you could give to your main function. And the way this works is that you specify what keys the dictionaries should have and what possible values this parameter should have and vary. And then what this dict list function will do is will just generate all the individual dictionaries for you. And there is also some nice functionality to only include the particular parameter name if a previous parameter name is included and stuff like that. You could check online for more details. On the other side of the coin, after you have run and saved your simulations, you want to collect all the results in a data frame. There's a very nice and simple function, collect results, that scans a folder and collects all the saved simulations as a data frame. What is very cool about this function is that if some simulations have a name that doesn't exist, this name automatically gets the value missing for them. So this function does all of this for you with only one line of code. Okay, so now this brings me to the end of this presentation. I want to show a recap of the tips that I have collected for reproducible science. I hope you already knew all of this. That's my hope. But if you don't, I really hope that you will embrace some of them and that they will be useful for you. And this way you can make nice reproducible science, or more reproducible that you already do. Have a look at Dr. Watson. I'm really proud of this project, and I think the other developers are too. It really has genuinely helped me a lot, and so has done to other scientists, friends of mine that use it. I want to say that these slides are part of a workshop that is general about good scientific code that is online and on YouTube. And I would be very happy if you can contribute, or just tell me. You don't have to contribute. You can just tell me the tips you use and you have found that make reproducible science easier and how you tackle reproducibility. And feel free to just send me your tips or even directly make them as a pull request to this repository. I'm very happy to learn more about the subject. So thanks very much. And thanks to Thomas for inviting me.